The monumental engineering achievements of ancient civilizations, from the awe-inspiring Great Pyramid of Giza to the vast Roman aqueduct networks and the earthquake-proof fortresses of the Inca, have long captured the human imagination. These feats are often perceived as unthinkable, given the limitations of pre-industrial technology, leading to popular but unfounded theories of lost super-technology or extraterrestrial intervention. A thorough analysis of the available archaeological and historical evidence, however, reveals a more compelling and grounded explanation. The mastery of these projects was not the result of magical or unknown forces, but a sophisticated fusion of refined intellectual principles, an unparalleled understanding of materials science, and a complex, centralized social organization. The great engineering feats of the ancient world were not constructed by chance or brute force alone. They were the physical manifestation of a profound understanding of mathematics and geometry. Initially, this knowledge was practical, developed by cultures such as the Babylonians and Egyptians for pragmatic purposes like measuring fields, calculating taxes, and building structures. However, a pivotal intellectual shift occurred with the rise of Greek civilization. Figures like Euclid collected and systematized centuries of scattered geometric facts into a logical, axiomatic framework. The Great Pyramid of Giza stands as a testament to this applied knowledge. Its base sides, each over 700 feet long, differ by no more than 8 inches, representing a margin of error of less than 0.1%. More remarkably, the pyramid is oriented to true north, with an error of only 3/60ths of a degree, a precision that is challenging for even modern builders to match. The precise alignment of many ancient structures with celestial bodies was not merely a religious or aesthetic choice. It was a critical, practical, and symbolic act. Egyptian astronomers could find true north by using a simple plumb line to align 2 specific circumpolar stars, Kochab and Mizar, when one was positioned directly above the other in the night sky. Modern astronomical calculations have shown that the celestial North Pole was perfectly positioned between these 2 stars around 2467 BC, a date that falls squarely within the estimated construction period of the Great Pyramid. Ancient civilizations developed a deep understanding of their local environments and resources. Roman concrete was a complex mixture of lime mortar, volcanic ash, and seawater, giving it remarkable strength and durability, with the ability to set and harden even underwater. The Inca developed earthquake-resistant dry stone masonry, with stones cut so precisely that a piece of paper cannot be inserted between them. This design allows structures to absorb seismic shock, surviving earthquakes that have leveled later Spanish constructions built with mortar. By examining these projects through the lenses of mathematics, physics, materials, science, and social history, a new and more accurate narrative emerges, one that celebrates the true genius and enduring legacy of the architects of antiquity. The Great Pyramid of Giza, the last surviving of the 7 wonders of the ancient world, is a testament to extraordinary precision and a feat of logistics unmatched in antiquity. With a base measuring 756 feet by 756 feet and an original height of 481 feet, the structure contains over 2 million limestone blocks, each weighing an average of 3 tons. The primary material for the pyramid core was locally quarried limestone, while the pristine outer casing was made from white limestone transported from the Tura quarries, and harder red granite from Aswan was used for key internal chambers. A recent archaeological discovery of a ramp system in a Khufu-era alabaster quarry provides tangible evidence for this method, showing that a central ramp flanked by staircases and post holes was used to pull stone blocks up steep slopes of 20% or more. Modern experiments to replicate the feat have highlighted this challenge. A project to build a small step pyramid required the use of electric saws and a railway line to move stones, yet still struggled to transport the materials from the Nile to the building site, a task that took ancient Egyptians years to perfect. Roman engineering marked a significant conceptual shift from building singular sacred monuments to creating sprawling utilitarian infrastructure networks. Their aqueduct systems were a masterful application of gravity and resource management, moving water over distances of 50 to 60 miles using only a slight downward gradient. To traverse diverse terrains, Roman engineers developed underground tunnels, surface-level channels, and elevated arch bridges to span valleys. When bridges were impractical for deep valleys, they used high-pressure lead or stone pipes in inverted siphons to carry water across. A key to the durability of Roman infrastructure was their revolutionary building material, concrete made from lime mortar, volcanic ash, and seawater. This unique composition gave it remarkable strength and durability, with the ability to set and harden even underwater. The material longevity is a result of a self-healing mechanism, where tiny lime clasts within the mixture dissolve and react to fill cracks with calcium carbonate, and ongoing pozzolanic reactions that continue to strengthen the material over time. The monumental structures of the Inca, particularly the fortresses of Sacsayhuaman and the city of Machu Picchu, represent a profound example of engineering designed in harmony with a hostile natural environment. The massive stones, some weighing over 100 tons, are meticulously cut into complex, irregular shapes and fitted together without any mortar. The precision of this jigsaw puzzle masonry is so exact that a piece of paper cannot be inserted between the stones. This design allows the structures to absorb the shock of seismic activity, surviving earthquakes that have leveled later Spanish constructions built with mortar. The conventional explanation involves labor-intensive methods such as pecking and grinding with hammerstones and chisels, or stone splitting using wooden wedges and water. The use of natural bedrock as the foundation for buildings further stabilized the structures, blending the built environment with the surrounding landscape. The true mastery of the Inca lay not in a superior technology, but in a deep, intuitive understanding of their local geology and a hyper-specialized adaptation to it. The lack of modern tools forced them to innovate in a way that prioritized structural resilience over speed or ease of construction. The ability to create a solution that remains effective for centuries, using only locally available resources, demonstrates a level of genius that we often overlook when we focus on what they lacked rather than what they perfected. However, the true unthinkable feat of these monuments was not the engineering itself, but the unparalleled logistics and project management required to sustain such operations for decades. The enduring belief that the Egyptian pyramids were built by a massive enslaved workforce is largely a misconception perpetuated by the ancient Greek historian Herodotus and later sensationalized by Hollywood films. Herodotus lived thousands of years after the pyramids were constructed, and modern archaeological evidence has overwhelmingly debunked his account. Instead of a slave camp, excavators at Giza have uncovered the remains of a purpose-built village that housed and fed the workers. The site contains barracks, bakeries, and food storage facilities, with evidence showing the workers were well fed on a diet that included prime cuts of meat and bread. Workers who perished on site were buried in tombs near the pyramids, furnished with supplies for the afterlife, an honor that would have been unlikely for a slave population. Graffiti left by work crews in the pyramids, such as the Friends of Khufu gang, points to a sense of camaraderie and pride in their work, not resentment. The workforce was not a single monolithic group, but likely a combination of full-time salaried employees and temporary conscripted laborers who worked in shifts, possibly as a form of national service or a labor tax. This highly organized, centralized social structure, which mobilized and sustained a specialized workforce of an estimated 20,000 to 30,000 individuals, was arguably the most impressive feat of all. For Roman projects, surveyors known as grammatici used tools like the groma to chart the straight lines of roads, while a wide range of skilled workers, including architects, engineers, stonemasons, carpenters and bricklayers, performed the construction. The ruins of Pumapunku in Bolivia present one of the most compelling examples of ancient engineering, with massive blocks cut with unprecedented geometric precision. The perfect 90-degree angles, intricate notches and drill holes look so machined that they seem impossible to have been made with simple stone tools. However, a simple tool, applied with a brilliant, painstakingly slow and highly skilled technique, could produce a flawless result. Alternative theories like the geopolymer hypothesis suggest stones were cast rather than carved, but these remain highly controversial and lack the archaeological evidence that would support such revolutionary claims. Whether conventional explanations or alternative theories prove correct, the ultimate lesson remains the same. Ancient builders were not primitive. They were masters of their materials and environment. Their solutions were often so elegant and specialized that we struggle to comprehend them from our modern perspective, leading us to seek extraordinary explanations for what was actually extraordinary human achievement. The unthinkable engineering feats of ancient civilizations were not the work of a lost super race or alien technology. They were the logical and magnificent result of human ingenuity under different, yet equally challenging constraints. Ancient builders made a pivotal leap from a purely empirical understanding of their world to a theoretical and abstract one, applying principles of geometry, physics, and astronomy to design with a level of precision that we still struggle to match. They demonstrated a profound understanding of materials, innovating with substances like Roman concrete for durability and creating earthquake-resistant dry stone masonry perfectly suited to its environment. Perhaps the most critical factor was the social engineering required to mobilize, manage, and sustain a specialized labor force on a colossal scale. This social mastery was as essential to the success of the projects as the technical knowledge. The legacy of these ancient architects is a powerful reminder that true strength lies not just in the tools we use, but in how we apply the laws of nature and how we organize ourselves to meet a challenge. The endurance of their structures speaks to a value we are only now re-embracing, a focus on longevity, durability, and a deep respect for the fusion of art, science, and the natural world. Their achievements challenge us to look beyond simple answers and to appreciate the profound intellectual and societal achievements that transformed raw materials into timeless wonders, reminding us that the greatest mysteries of the past reveal not impossible technologies, but the unlimited potential of human collaboration, ingenuity, and determination.